So in this video, we're going to look at a couple different additional examples of creating vectors using the colon operator along with linspace. So examples, I should say 2 through 4, not 2 through 3. I thought I was going to do 4, but those get to be a little bit long of videos. Example 2, just assume that you wish to plot a sinusoidal function of specified frequency, like we did a lot in the last module. Can we describe the general trade-off between having fewer points within our time vector? More formally, that is denoted as having inadequate temporal resolution or a sampling rate that's too low versus actual too many. So what's basically the trade-off that results with respect to the performance of our code from an execution point of view and an actual utility point of view? And I'll show you what I mean by that in a minute. So I think it's always good to walk back through the example of how you actually would generate a vector corresponding to the values of a sinusoid and then actually make the plot in MATLAB. Just pick any frequency that you like. Maybe it is 100 hertz. So let's say 100 hertz frequency. And then remember that when you're using the colon operator, in order to define the discrete values of time for which you're going to make the plot, it's good to do it with respect to a period. So I would just say the period is 1 over the actual frequency. And then since I'm going to be using the colon operator, I need to define the adjacent step between elements in my array. So I could say delta t here is going to be nothing more than t divided by, and this is the number that I have to pick. It's basically going to determine how densely I'm making my sample in time. So let's just start with 2. So let's just say that this defines how many samples per period. So this isn't going to be very densely sampled at all. Then what I want to do is create my value of time vectors for which I'm going to generate the plot. I specify my starting value. I've defined my step between each adjacent element in terms of the period. I'm calling that delta t as a variable. And say I just wanted to plot 2 periods of this sinusoid. So I go to 2 times t. So this is going to just basically create a vector of time values from 0 to 2 periods at the resolution of delta t. Now I need to define the actual values of the signal that I want to plot. Let's just keep it unity amplitude to make it easy. So we won't have a value out in front. It will just be y equals sine of 2 times pi times f times that actual t value. That is the general form of a sinusoid with unity amplitude, meaning that the amplitude is 1 and no phase shift. And then let's just plot t versus y. And let's see what actually happens in this case. And remember, we're terminating all of the commands with semicolons just to minimize any output on the command window when we actually execute the script, because the end user here wouldn't care whether or not what we're doing to plot this sinusoid. They just want to see the plot of the sinusoid. So this looks like absolute garbage when we make the plot. And if you look at the actual amplitude values, 4 times 10 to the negative 16th, that's effectively 0 within rounding error, right? So really what is probably happening here, and if you think about the way a sinusoid works, we're just sampling the zeros by sampling at a half period, because a sinusoid starts at a 0, a quarter period through, it's at its maximum value, half period through, it's back at 0, then minimum, then 0. So we're just hitting all the zeros. So if we go to 4 samples per period, what's going to happen now? Well, we won't only hit all the zeros, still hitting the zeros, but we're also hitting the maximum and minimum values. So this still doesn't look like anything like a sinusoid. So what if rather than having 4 samples per period, we divided our step up into 8, which will allow us to have 8 samples per period? We're going to get something that looks a little bit more like a sinusoid. It's getting there, but it's still not nice and smooth at the top. And I'm kind of moving up in a geometric progression by a factor of 2. Let me just take a bigger jump there. Say we went to, I don't know, t divided by 20 samples per period. If you notice in this case, right, we're getting towards a very nice and smooth function. However, what's happening is the amount of values that we're storing in our time vector along with our y vector is increasing each time. So hopefully if you want to rewind and go back and look at the size of t, now that's 1 divided by 41 versus, of course, when it was just t divided by 2, right, that was only actually a 5-element array. So the trade-off is, well, you might say, well, why wouldn't from the start I'll just go to 1,000 samples per period? Of course, you're going to get a really nice and smooth graph in that case. However, the actual amount of data that you're storing in both your t vector along with your y vector is very, very large. So not only is that may that be inefficient from an actual storage point of view with respect to conserving your memory, but also from an execution point of view, when you run your code, it will take a larger amount of time. Now, in this particular case, that's going to be trivial because we have a lot of memory on all of our modern machines, and we're not doing much here in terms of the processing of these big arrays other than generating visualizations. So we're not going to actually notice the difference in those trade-offs, but it's something that I want you to be aware of. You wouldn't want to just drive this to infinite resolution to generate the perfect graph. Because after you pass a certain point, from a visual perspective, the end user won't be able to see the difference in the smoothness of the graph, but you are increasing the storage requirements and the time of execution requirements. And remember that the way that MATLAB is actually plotting this is it's only plotting the actual values for the discrete points in time for which the vector is defined, and then it's doing what's known as linear interpolation between them. So basically, when you only have the zeros and the maximum and the minimum values, it just looks like a triangle wave because it's just drawing a straight line between those points. But as the points become more densely and densely spaced, you're going to get a nicer and smoother representation that looks like you typically represent a sinusoid when you sketch it like in a trigonometry class or something. So example 3 here, generate an array of 10 equally spaced values between 5 and 9, demonstrate an approach for determining the spacing between elements by indexing to adjacent points within your resulting array. So whenever you're talking about having equally spaced values, you know how many you want, you know the start point and the end point. That's not going to be a good case to use the colon operator. The colon operator is good when you know the start and the end point and you know the step that you want between each adjacent point. Here we know we just need 10 points, whatever step is necessary, in a vector between 5 and 9. So the function that we want to use in that case is actually linspace. If you don't remember how to do it, I'm just going to do this one on the command line. So I'm going to close that figure. I'm going to expand my command line a little bit. I'm going to actually clear it out, CLC. I'm going to clear my memory as well. And I'm just going to create an array. I'll call it X. And we wanted this to go. Well, before we do that, let's actually let me show you how to use kind of the real-time help that you get when you start to type a function. So if you notice, if you just start to type linspace, it will autofill, and it gives you a hint here that says it's generate a linearly spaced vector. And then if you use the standard actual function notation of opening with a parentheses, starting to pass the arguments in, notice that we get some hints here. It tells us that these are a pair of scalars, x1, x2, and then we have this second argument n. So if we're familiar with linspace, you probably would automatically have your memory jarred and say, oh, I specified the actual start point, the stop point, and then the number of steps. But if you don't remember that, in addition to actually searching on the internet, you can just use the help function locally here on the actual command window and just scroll up, and you see here, linspace x1, x2, n generates n points between x1 and x2. That's exactly what we thought. So I'll define a new variable name for my vector, and I'll type linspace. We wanted our actual vector to start at 5 and end at 9 and have 10 points. So let me do that. And I will not terminate it by a semicolon, just to basically show that this starts at 5 and ends at 9 and it has 10 points to it. Now, the second part of the question is, can you find the spacing between adjacent elements using indexing? Well, if you think about it, the spacing between any two adjacent elements is going to be the same. So if you just index into one particular element, say the second element here, remember that MATLAB is a one-base index, so that's going to grab this 5.4 repeating, and then you subtract away the actual value of x1, that's going to tell you the spacing between elements. However, I didn't have to pick 2 and 1. I could have picked 4, and since I typed 4 and 3, I would get the same results. Another very useful function that you might actually use often in MATLAB is this diff function. And what that will do is it will compute the difference between the values of the array between each of the adjacent points. So since x had 10 elements in it, if you pass the diff function into x, it will take the difference between the values of each of the adjacent points. That will only be 9 long, since when you take a difference, you kind of throw one away. And notice that in this case, each of these values is the same, not surprisingly, because that's what linspace actually does, is generate evenly spaced values between a start point and an end point, versus the colon operator, which generates values at a user-specified interval between a start point and an end point.